Imagine standing in the middle of a field on the darkest night you have ever experienced. No city lights, no moon. Just you, the ground beneath your feet, and above you, a river of light so vast, so impossibly wide, that your brain simply refuses to process what it is seeing. That pale, shimmering band stretching from one horizon to the other is not a cloud. It is not a trick of your eyes. It is the galaxy you live in. Every single star you can see with your naked eye, every constellation you have ever learned the name of, every ancient myth painted across the night sky, all of it, every last point of light, belongs to the same enormous structure. And you are inside it. You have always been inside it. You were born inside it, and you will die inside it. And the extraordinary, terrifying, mind-bending truth is that you will never, not even for a single second of your life, be able to fully see it from the outside. That alone should stop you cold. We are talking about the Milky Way. And before you decide that you already know what the Milky Way is, before you picture that familiar diagram from a school textbook showing a flat spiral with a bulge in the middle and some labeled arms, I want you to stop and genuinely ask yourself, do you actually know what the Milky Way is? Do you know what it contains? Do you know what is hiding at its center? Do you know what it has done, what it has destroyed, what it has swallowed, what it is currently doing right now as you listen to these words? Because the Milky Way is not a peaceful, stable, beautiful structure floating quietly through the cosmos. It is an ancient, violent, cannibalistic entity that has been consuming other galaxies for billions of years, that harbors at its very core a monster so extreme that the laws of physics as we understand them break down in its presence, and that is, at this very moment, on a collision course with another galaxy that will reshape everything. Everything in a catastrophic, slow-motion cosmic event that will last billions of years. And that is just where we begin. We are going to take 50 facts about the Milky Way, and we are not going to skim the surface. We are going to go deep. Deeper than most people are willing to go. We're going to explore the science, yes, but we are also going to explore what that science means, what it feels like, what it reveals about the strange and terrifying place we call home. We are going to ask hard questions. We are going to sit with uncomfortable answers. We are going to encounter ideas so large that they push the limits of human imagination, and then we are going to push further. So take a breath. Look up if you can, and let us begin. The Milky Way is old. Not just old in the way that mountains are old, or civilizations are old, or even in the way that the Earth itself is old. The Milky Way is approximately 13.6 billion years old. To put that in perspective, the universe itself is estimated to be about 13.8 billion years old. That means the Milky Way began forming almost immediately after the Big Bang, almost at the very beginning of everything. When the universe was still an infant, barely 200 million years into its existence, the first seeds of what would become our galaxy were already beginning to take shape. The very oldest stars we have found within the Milky Way are nearly as old as the universe itself, ancient stellar fossils from an era so remote that the concept of time barely applies in any way that makes sense to a human mind. Ask yourself this: if the Milky Way is almost as old as the universe, what was it like in those first billions of years? What kind of place was it before Earth existed? Before the Sun existed? Before any rocky planet anywhere in this galaxy existed at all? The answer is both humbling and terrifying. The early Milky Way was not the structured, elegant spiral we know today. It was chaotic, dense, violent beyond any scale of violence we can comprehend from our vantage point on a small rocky world in a quiet suburban region of the galaxy. The early Milky Way was a place of constant, massive star formation, where enormous stellar giants were being born and dying in explosions, supernovae, so powerful that they seeded the surrounding gas clouds with heavy elements, the building blocks of everything that would come later, including us. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen in your lungs was forged inside a star that lived and died before our sun was ever born. The Milky Way is not just our home. It is our parent. It is our origin. It is the source of the very matter that constitutes every cell of every living thing on this planet. That is not poetry. That is chemistry. That is physics. That is the literal, documented, scientifically established truth of where you came from. Now let us talk about size. Because until you genuinely grapple with the size of the Milky Way, nothing else about it will land with the weight it deserves. The Milky Way is estimated to be approximately 100,000 light-years in diameter. Some recent studies suggest it may be even larger, possibly 160,000 light-years or more when you factor in the outer disk. A light-year is the distance light travels in 1 year. Light moves at roughly 300,000 kilometers per second. In 1 second, light can travel around the Earth 7.5 times. In 1 year, it travels about 9.5 trillion kilometers. Now multiply that by 100,000. That is the width of the Milky Way. That is the distance from one edge of our galaxy to the other. And our solar system, our sun, with all its planets, all its asteroids, all its comets, the entire solar system that we think of as our cosmic neighborhood. It sits about 26,000 light-years from the center. We are not at the center. We are not at the edge. We are somewhere in the middle of a spiral arm, in what astronomers sometimes describe as the cosmic suburbs, far from the dense, violent galactic core, far from the sparse outer reaches, in a relatively calm and stable region that, as we will explore later, may be one of the reasons life was able to develop here at all. But do not let the word suburbs fool you into thinking our neighborhood is boring. It is not. The Milky Way contains between 100 billion and 400 billion stars. The uncertainty in that number is itself staggering. We are not sure whether there are 100 billion or 400 billion stars, and that range of uncertainty spans 300 billion suns. Think about that. 300 billion suns worth of uncertainty. The reason for this range is partly that we cannot see the entire galaxy from our position inside it. Much of it is obscured by dust and gas, and partly that there are enormous numbers of very faint, dim stars that are difficult to count even with our best instruments. But even the lower estimate of 100 billion is a number that defies intuitive comprehension. If you tried to count to 100 billion, counting one number per second without stopping, without sleeping, without eating, it would take you over 3,000 years. 3,000 years of non-stop counting just to reach the lower estimate of the number of stars in our galaxy. And the Milky Way is not even a particularly large galaxy. It is considered a medium to large spiral galaxy, but in the grand zoo of galaxies in the universe, it is unremarkable in size. There are galaxies that dwarf it completely. IC 1101, the largest known galaxy, is estimated to be about 6 million light-years in diameter. That is 60 times wider than the Milky Way. The universe contains an estimated 2 trillion galaxies, though more recent studies have pushed that number even higher. Our galaxy, vast as it is one of 2 trillion. We are not special in terms of scale, and that realization, when you let it fully sink in, is one of the most profound things a human being can experience. Here is something that takes even seasoned astronomers a moment to appreciate. The Milky Way is not just stars. In fact, if you were to add up all the mass of all the stars in the Milky Way, all 400 billion of them, they would account for only a fraction of the total mass of the galaxy. The vast majority of the Milky Way's mass, somewhere around 85 to 90% of it, is composed of something we cannot see, cannot detect directly, cannot interact with in any meaningful way with our instruments. We call it dark matter, not because it is mysterious in a poetic sense, though it is deeply mysterious, but simply because it does not emit, reflect, or absorb light. It is invisible, and yet it is everywhere. Dark matter forms a vast, invisible halo that envelopes the entire Milky Way, extending far beyond the visible disk of stars and gas, and its gravitational influence is what holds the galaxy together. Without dark matter, the stars on the outer edges of the Milky Way would fly off into intergalactic space. They rotate too fast for ordinary matter alone to explain. The only explanation that fits the observations is that there is something massive and invisible providing additional gravitational glue. Ask yourself this and sit with it for a moment. What does it mean that the majority of our own galaxy, our home, is made of something we cannot see, cannot touch, and do not fully understand? We do not know what dark matter is. We have theories. The leading candidates include hypothetical particles called WIMPs, weakly interacting massive particles, and axions, and sterile neutrinos, among others. But none of these have been definitively detected. Decades of experiments, some of the most sophisticated and expensive scientific endeavors ever undertaken, have so far failed to catch a single dark matter particle in the act. And yet the evidence that it exists is overwhelming. It comes from the rotation curves of galaxies, from gravitational lensing, from the structure of the cosmic microwave background, from the large-scale structure of the universe itself. Dark matter is one of the most well-evidenced and least understood phenomena in all of science, and it makes up most of your galaxy. Now let us go to the center. The center of the Milky Way is in the direction of the constellation Sagittarius, approximately 26,000 light-years away from us. You cannot see the galactic center with your naked eye, not because it is not bright enough, but because there are enormous clouds of dust and gas between us and it that absorb visible light completely. The galactic center is one of the most extreme environments in the known universe. It is dense with stars, packed so tightly that if you were a planet orbiting a star at the galactic center, your night sky would be blazing with light. Thousands of stars within the distance that separates us from our nearest stellar neighbor, Proxima Centauri, which is 4.2 light-years away. At the galactic center, stars are packed so tightly that they orbit each other in tight, fast loops, whipping around the central region at extraordinary speeds. And at the very center of all of this, at the precise heart of the Milky Way, there is something called Sagittarius A star. It is a supermassive black hole. It has a mass of approximately 4 million times the mass of our Sun. 4 million solar masses, compressed into a region roughly the size of our solar system, perhaps smaller. Its event horizon, the point of no return, the boundary beyond which not even light can escape, is about 24 million kilometers across. For comparison, the Sun is 1.4 million kilometers in diameter. So the event horizon of Sagittarius A star is roughly 17 times wider than the Sun. And the Sun, remember, could fit 1 million Earths inside it. This is the scale of the beast at the center of our galaxy. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole, M87 star, located in the galaxy Messier 87, 55 million light-years away. The image showed a glowing ring of superheated matter surrounding a dark central shadow. It was a historic achievement, one of the greatest in the history of observational astronomy. But that black hole is a giant, with a mass of 6.5 billion solar masses, more than 1,000 times more massive than Sagittarius A star. In May 2022, the Event Horizon Telescope team released the first ever image of Sagittarius A star itself. Our own galactic center, our own black hole. The image was technically extraordinarily difficult to produce. Sagittarius A star is much closer than M87 star, but also much smaller, and its surrounding material changes on much faster timescales, making it harder to image clearly. But there it was. A glowing, fuzzy ring of light, surrounding a region of darkness at the center of our galaxy. For the first time in history, human beings looked directly at the black hole that lives at the heart of the Milky Way. The fact that we are alive, that we exist on a planet that has life, and that the black hole at the center of our galaxy is relatively quiet, currently not actively feeding in a violent way, is not a coincidence in the sense that one lucky roll of cosmic dice produced it. It may be deeply connected to the structure and history of our galaxy in ways we are only beginning to understand. During the early history of the Milky Way, Sagittarius A star was likely far more active. It probably went through periods of intense activity, consuming gas and dust and releasing enormous amounts of energy in the form of jets and radiation that could have been profoundly harmful to any life attempting to develop in the galaxy at that time. The fact that it is quiet now, in the current epoch of the universe's history, may be one of the reasons why we are here to observe it. Let us talk about the arms. The Milky Way is a barred spiral galaxy. That is its official classification. The spiral part means it has arms, curved structures of stars, gas, and dust that spiral outward from the central region. The barred part means there is a bar-shaped structure of stars at the center, through which the spiral arms originate. The Milky Way has four main spiral arms: the Perseus arm, the Norma arm, the Scutum Centaurus arm, and the Sagittarius arm. There are also smaller partial arms called spurs, and our solar system sits in one of these, the Orion spur, also called the Orion arm, which is a minor arm or spur connecting the Perseus arm and the Sagittarius arm. We do not live in a major arm. We live in a relatively minor structure, a small branch off one of the main highways of the galaxy. Think of it like living in a small side street branching off a major road in a large city. The traffic and density of the main roads are elsewhere. Our neighborhood is quieter, less dense, and possibly safer for that reason. The spiral arms are not solid objects, like spokes on a wheel. They are more like traffic jams, regions of higher density through which stars and gas pass. The arms themselves are density waves, regions where matter is compressed as it moves through, triggering star formation. Stars are not permanently located in a specific arm. They move in and out of the arms over time as they orbit the galactic center. Our Sun takes approximately 225 to 250 million years to complete one full orbit around the center of the Milky Way. This period is sometimes called a cosmic year or a galactic year. In the entire history of life on Earth, about 3.8 billion years, the Sun has completed only about 15 to 17 orbits around the galactic center. In the entire history of the Earth itself, 4.5 billion years, we have gone around the galaxy roughly 18 to 20 times. Everything that has ever lived on this planet, every species that has ever evolved, every organism that has ever drawn breath, has existed within a very small arc of the Sun's galactic journey. Ask yourself, what was the Milky Way like the last time our solar system was in the same position in its orbit? That would have been about 250 million years ago, approximately when the Permian extinction event was happening on Earth, the largest mass extinction in the planet's history, when over 90% of all marine species and 70% of all land vertebrate species were wiped out. Coincidence? Almost certainly. But the cosmic context is breathtaking. Now, here is something that will genuinely rearrange your sense of motion. At this very moment, as you sit or stand wherever you are moving at extraordinary speed through the universe. Not because you are in a car or on a plane, but simply because you exist on a planet that is doing several things at once, simultaneously, all the time. The Earth is rotating on its axis at roughly 1,670 kilometers per hour at the equator. The Earth is orbiting the Sun at approximately 107,000 kilometers per hour. The Sun, along with the entire solar system, is moving through the Milky Way, orbiting the galactic center, at approximately 828,000 kilometers per hour. That is 230 kilometers per second. And the Milky Way itself is moving through the universe toward a structure called the Great Attractor, at roughly 2 million kilometers per hour relative to the cosmic microwave background. Add all of that up. You are not sitting still. You have never sat still. Not for a single nanosecond of your life. You are hurtling through space at speeds that would carry you from one side of the Earth to the other in a matter of seconds, and you have absolutely no sensation of this because there is no fixed reference point in the universe against which to feel it. The Great Attractor deserves its own moment of attention here. It is a gravitational anomaly, a region of space toward which the Milky Way, along with hundreds of other galaxies in our local supercluster, appears to be moving. It sits at a distance of approximately 250 million light-years from us, in the direction of the constellation Centaurus. For a long time, astronomers could not study it directly because it lies in the zone of avoidance, the region of sky obscured by the disk of the Milky Way. What exactly lies there remains somewhat mysterious. It appears to be a massive concentration of matter, possibly including a vast supercluster of galaxies. The Laniakea supercluster, the enormous supercluster of which the Milky Way is a part, has its attractor point at this location. Laniakea, whose name comes from the Hawaiian for immeasurable heaven, is 500 million light-years across and contains the mass of 100 quadrillion suns. The Milky Way is one tiny member of this vast gravitational congregation. We are being pulled toward something we can barely see and do not fully understand, and we have been for billions of years. Let us shift to something that might genuinely disturb you in a way that no horror story ever could. The Milky Way is a cannibal. It has been eating other galaxies for its entire history, and it is still doing so right now. The process is called galactic cannibalism, or more formally, galaxy merging, and the evidence for it is written all over the structure of our galaxy in ways that astronomers have been piecing together for decades. The stellar halo of the Milky Way, a vast, roughly spherical cloud of stars that surrounds the galactic disk, is populated with stars that do not belong to the original Milky Way. They are the remains of dwarf galaxies and star clusters that were gravitationally captured, pulled in, shredded apart, and absorbed by the Milky Way over billions of years. These stars were not born here. They were brought here by force. Their home galaxies dissolved into streams of stars that now orbit the Milky Way in long, looping arcs called stellar streams. One of the best examples of this process happening right now is the Canis Major dwarf galaxy, though it is so disrupted that whether it qualifies as a galaxy anymore is debatable. It sits about 25,000 light-years from our solar system, and it is currently being gravitationally stretched and shredded by the Milky Way, its stars being drawn into a long filament called the Monoceros ring that wraps around the outer disk of the Milky Way. The Sagittarius dwarf galaxy is another example. It is on a collision course with the Milky Way, swinging around and through the galactic disk in a long looping orbit, and each time it passes through, it loses stars to the Milky Way's gravitational grip. There are streams of Sagittarius stars stretching across the sky, the visible remnants of a galaxy being slowly consumed. In 2022, astronomers using data from the Gaia spacecraft, the European Space Agency's incredible star mapping mission that has catalogued the positions and motions of nearly 2 billion stars, announced the discovery of evidence for a major merger event that took place about 8 to 11 billion years ago. It was the merger of the Milky Way with a galaxy now called Gaia Enceladus or Gaia Sausage. This was a significant event. The smaller galaxy had a mass perhaps a quarter of the Milky Way's mass at the time, and its merger fundamentally shaped the structure of the Milky Way we know today, particularly its stellar halo and thick disk. The stars from Gaia Enceladus are still there, still orbiting in the halo, still distinguishable from native Milky Way stars by their chemical composition and orbital characteristics. The Milky Way absorbed this galaxy billions of years ago, and the evidence of that ancient crime is written in the motions of the stars above our heads. Here is a question for you to sit with. When we look at the stars in the night sky, some of those stars, the ones in the halo, the ones in long stellar streams, might be immigrants. Their home galaxy was consumed billions of years before the Earth even formed. They have been orphan stars for longer than our entire solar system has existed. How does that change the way you think about the night sky? The Milky Way has satellites. Just as the Earth has the Moon, and Jupiter has its many moons, the Milky Way has companion galaxies that orbit it, dwarf galaxies gravitationally bound to our galaxy. The most famous of these are the Large and Small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way that light up the night sky like broken-off fragments of the galactic river. The Large Magellanic Cloud is about 160,000 light-years away and is the fourth largest galaxy in the local group, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. The Small Magellanic Cloud is about 200,000 light-years away. Both are irregular dwarf galaxies, chaotic in structure compared to the elegant spiral of the Milky Way, their shapes distorted by the gravitational interaction with our galaxy and with each other. These two galaxies are connected to the Milky Way and to each other by the Magellanic Stream, a vast ribbon of gas stretching across 300 degrees of the sky, pulled out of both galaxies by gravitational interaction. This stream is thought to be feeding gas into the Milky Way, providing material for future star formation. The Magellanic Clouds also have their own star-forming regions. The Tarantula Nebula, in the Large Magellanic Cloud, is one of the most active star-forming regions in the entire local group, so bright that if it were as close to us as the Orion Nebula, it would cast shadows at night. The Tarantula Nebula contains some of the most massive stars known to exist, including our 136A1, which has a mass over 300 times that of the Sun, making it one of the most massive stars ever discovered. For a long time, astronomers assumed the Magellanic Clouds were permanent satellites of the Milky Way, on long, stable orbits that have been ongoing for billions of years. But recent measurements of their velocities suggest something surprising. They may actually be visitors. They may be moving too fast to be permanently bound to the Milky Way, and may have only recently, in cosmic terms, within the last few billion years, entered our gravitational neighborhood for the first time. If this is true, the Milky Way may eventually consume these galaxies too, but they might also escape. The future of the Magellanic Clouds is still an active area of research. The Milky Way is part of a larger structure called the Local Group. This is a collection of more than 50 galaxies, all gravitationally bound together, spread across a region roughly 10 million light-years in diameter. The three largest galaxies in the Local Group are the Andromeda Galaxy, also known as Messier 31, the Milky Way, and the Triangulum Galaxy, also known as Messier 33. The Andromeda Galaxy is the nearest large galaxy to the Milky Way, sitting approximately 2.5 million light-years away. It is visible to the naked eye from a dark location as a faint, elongated smudge in the constellation Andromeda. And remarkably, what you are seeing when you look at it is light that left the Andromeda Galaxy 2.5 million years ago. You are looking back in time every time you look at that smudge of light. The Andromeda Galaxy is slightly larger than the Milky Way, containing perhaps 1 trillion stars, though its total mass may actually be similar to or even less than the Milky Way when dark matter is accounted for. There is ongoing debate about which of the two galaxies is actually more massive. And here is where things become genuinely dramatic. The Andromeda Galaxy and the Milky Way are on a collision course. They are approaching each other at approximately 110 kilometers per second. In approximately 4 to 5 billion years, they will collide. This collision will not be like two billiard balls smashing into each other. Galaxies are mostly empty space. The distances between stars are so vast that in a galaxy merger, stars almost never actually collide with other stars. Instead, the two galaxies will pass through each other, their gravitational fields distorting and reshaping each other, flinging stars off into intergalactic space, triggering enormous waves of star formation as gas clouds collide and compress, and gradually, over hundreds of millions of years, merging together into a single, larger galaxy. Astronomers have even given this merged future galaxy a name: Milkomeda, a portmanteau of Milky Way and Andromeda. What will happen to our solar system during this collision? The honest answer is, probably not much, directly. The Sun and its planets are unlikely to come close enough to another star for anything dramatic to happen. But the gravitational perturbations could alter the Sun's orbit, moving it to a completely different region of the merged galaxy. The night sky will look completely different. Not just different, but unrecognizable. The familiar constellations will be warped beyond recognition as nearby stars shift their positions, and the galactic structures visible in the sky will be chaotic, twisted rivers and loops of stars and nebulae on a scale that no human eye has ever seen. If any beings are alive on Earth or its successor worlds during this period, and at 4 to 5 billion years in the future, that is a vast question, they will have a view of the sky that is arguably the most spectacular in the entire history of our planet. Ask yourself, do you think there will be life on Earth in 4 billion years? What form might it take? And would it understand what was happening to the sky above it? Now let us talk about something that sounds like science fiction but is established science fact. The Milky Way has a thick disk and a thin disk. The disk of the galaxy, the flat, spiral structure where most of the stars, gas, and dust are located, is actually two overlapping components with different properties. The thin disk is roughly 1,000 light-years thick, contains most of the youngest stars and most of the interstellar gas and dust, and is where most active star formation is occurring. The thick disk is roughly 3,000 to 4,000 light-years thick, contains older, more metal-poor stars. Stars formed earlier in the galaxy's history when the interstellar medium had not yet been enriched by many generations of stellar nucleosynthesis, and has a different chemical composition and different orbital characteristics from the thin disk stars. The two disks merge seamlessly, but they represent two different epochs of the galaxy's history. The thick disk being a relic of an earlier, more chaotic period of formation, and the thin disk representing the more settled, mature galaxy that has developed over the last few billion years. The disk of the Milky Way is not perfectly flat. It is warped. Like the brim of an old hat that has been bent out of shape over many years, the outer disk of the Milky Way is buckled and twisted, curving upward on one side and downward on the other. This warp was known for decades, but its cause was debated. Recent studies, using data from the Gaia spacecraft, have suggested that the warp is not a static feature, but is actually precessing, rotating, slowly changing its orientation over time, like the wobble of a spinning top. The likely cause is the gravitational interaction with the Magellanic Clouds, whose passage around the outer edges of the Milky Way may be setting up a kind of gravitational ripple in the disk. The Milky Way is not a static, perfect structure. It is dynamic, imperfect, and in a constant state of change. Here is something that will reframe every starry night you have ever experienced. When you look at the night sky and see stars twinkling, you are not seeing those stars as they are right now. You are seeing them as they were in the past, because light takes time to travel, and the distances involved are so vast that the light from even nearby stars is ancient by the time it reaches your eyes. The nearest star to us, Proxima Centauri, is 4.2 light-years away, so you are seeing it as it was 4 years ago. The next nearest bright star visible to the naked eye, Alpha Centauri, is 4.4 light-years away. Sirius, the brightest star in the night sky, is 8.6 light-years away. You are seeing it as it was nearly 9 years ago. Betelgeuse, the red supergiant in Orion, is about 700 light-years away. You are seeing it as it was during the Middle Ages on Earth. The stars of the Milky Way visible in the galactic band are typically hundreds to thousands of light-years away. When you look at the heart of the Milky Way, at the faint glow of the galactic center, you are seeing light that left that region 26,000 years ago, when anatomically modern humans were living in caves and painting on walls. The night sky is not a snapshot of the universe as it is now. It is a collection of messages from the past, each one delayed by the travel time of light, each star a time capsule from a different era. Now here is a question that should haunt you a little. Some of the stars you see in the night sky may no longer exist. They may have exploded as supernovae, or expanded into red giants, or otherwise changed dramatically, and the news of that change simply has not reached us yet. We would not know for years, decades, centuries, or millennia. We are watching a past that may already be radically different in the present. Let us talk about nebulae, because they are among the most visually spectacular features of the Milky Way, and they tell a story about the galaxy's past and future that deserves to be told. A nebula is a cloud of gas and dust in interstellar space. Some nebulae are the birthplaces of new stars, regions where gravity is causing gas to collapse inward, heating up as it does, eventually triggering nuclear fusion and giving birth to a new star. The most famous of these stellar nurseries in the Milky Way is the Orion Nebula, visible to the naked eye as the fuzzy middle star in Orion's sword. It is about 1,300 light-years away, 40 light-years across, and contains thousands of young stars in various stages of formation. It is, in a very real sense, a factory, a place where the raw materials of the galaxy are being assembled into new suns, some of which will likely have planets, some of which might, over billions of years, develop conditions suitable for life. Other nebulae are the graves of stars. When a star like our Sun reaches the end of its life, after billions of years of burning hydrogen and helium in its core, it expands into a red giant and then, in a relatively gentle death, sheds its outer layers as a glowing shell of gas called a planetary nebula. A name that is historically confusing because planetary nebulae have nothing to do with planets. They were named by early observers who thought they looked like planets through small telescopes. These shells of expelled gas, illuminated by the ultraviolet radiation of the hot stellar remnant. A white dwarf, at their center, forms some of the most beautiful structures in the galaxy. The Ring Nebula, the Cat's Eye Nebula, the Butterfly Nebula. Each one is the ghost of a dead star, a final exhalation of matter that will eventually disperse into the interstellar medium and be recycled into future generations of stars and planets. And then there are supernova remnants, the aftermath of the most violent stellar deaths. When a massive star, many times more massive than our Sun, exhausts its nuclear fuel, it collapses catastrophically and then explodes in a supernova, briefly outshining entire galaxies and ejecting matter at a significant fraction of the speed of light. The expanding shell of material, a supernova remnant, can persist for thousands of years, heating and enriching the surrounding interstellar medium. The Crab Nebula, 7 light-years across and still expanding, is the remnant of a supernova that was observed by Chinese and Arab astronomers in the year 1054 AD. At its center is a pulsar, a rapidly spinning neutron star, the dense collapsed core of the original star, spinning 30 times per second and beaming radiation across space like a cosmic lighthouse. The idea that an event observed by medieval astronomers less than 1,000 years ago produced something that is still visibly expanding and glowing in the sky today is a powerful reminder that the galaxy is not a finished, static thing. It is alive with processes happening on all timescales, from the millisecond pulses of a neutron star to the billion-year arcs of galactic mergers. The Milky Way has a mass that is genuinely difficult to pin down precisely, and the uncertainty itself is interesting. Estimates range from about 800 billion solar masses to as much as 1.5 trillion solar masses, with more recent studies tending toward the lower end of that range. The mass of the visible matter, stars, gas, dust, accounts for only a fraction of the total. The rest, as we have discussed, is dark matter. The mass of the Milky Way is important because it determines the strength of its gravitational influence, which in turn determines how many satellite galaxies it can hold, how it interacts with other members of the local group, and ultimately its future trajectory in the universe. A key measurement came in 2019, when astronomers published a study using the velocities of distant globular clusters, ancient, dense balls of stars that orbit the Milky Way in the halo, to constrain the total mass of the galaxy more precisely. The result was approximately 1.5 trillion solar masses, but with significant uncertainties. Nailing down the mass of a galaxy from the inside is a genuinely hard problem, analogous to trying to figure out the size of a forest while standing in the middle of it. Globular clusters deserve more than a passing mention here. The Milky Way has about 150 to 200 known globular clusters, ancient spherical collections of typically hundreds of thousands to millions of stars, gravitationally bound into tight balls, orbiting the galaxy in the halo and in the outer regions of the disk. These clusters are among the oldest objects in the galaxy. Some of them have ages of 12 to 13 billion years, almost as old as the universe itself. They formed in the earliest phases of the galaxy's history, possibly even before the Milky Way had settled into its spiral form. The stars within globular clusters are extraordinarily densely packed near the center. In the core of a typical globular cluster, stars are separated by distances measured in light-weeks rather than light-years, making the stellar density millions of times higher than in the neighborhood of the Sun. If you were on a planet in the core of a globular cluster, the night sky would be blazing with the light of millions of nearby stars. Some astronomers have speculated that the stellar crowding in globular clusters would make planetary systems more difficult to maintain stably, due to gravitational perturbations from passing stars. But this is still an open question. Several globular clusters, it turns out, are not native to the Milky Way. They were brought here by other galaxies that were subsequently absorbed. Omega Centauri, the largest globular cluster associated with the Milky Way, may actually be the former nucleus of a dwarf galaxy that was stripped of its outer stars and now orbits us as a remnant core. It is extraordinary in several ways. It is about 5 million solar masses, contains multiple stellar populations of different ages and chemical compositions, and may even harbor an intermediate mass black hole at its center. If Omega Centauri is a stripped galactic nucleus, it represents a fascinating case of a galaxy reduced to its most essential component, its densely packed inner core, everything else torn away by the Milky Way's gravity over billions of years. Here is something that should genuinely shift your perspective on the scale of empty space. The average distance between stars in the disk of the Milky Way, in a typical region like the solar neighborhood, is about 4 to 5 light-years. That is roughly 4 to 5 times the distance from us to Proxima Centauri. The disk is not a crowded place in any intuitive sense. If you were to scale down the sun to the size of a basketball, 24 centimeters across, the nearest star, Proxima Centauri, would be at a distance of about 6,500 kilometers away. At basketball scale, the nearest star to the sun is roughly the distance between New York and London. And between them, essentially nothing. A near-perfect vacuum. A handful of hydrogen atoms per cubic centimeter, on average. The galaxy, for all its stars, is almost entirely empty space. And yet that empty space is not nothing. Interstellar space is filled with the interstellar medium, a diffuse mixture of gas and dust, electromagnetic radiation, cosmic rays, and magnetic fields. The gas is mostly hydrogen, about 90%, along with helium and trace amounts of heavier elements. It comes in several phases. Hot, sparse gas heated by supernova shocks. Warm gas in typical HII regions. Cold, dense molecular clouds where star formation occurs. The dust component of the interstellar medium, tiny grains of silicates, carbon compounds, and ices, is crucial for shielding the interiors of molecular clouds from ultraviolet radiation, allowing complex molecules, including amino acids and other organic compounds, to form on the surfaces of these grains and in the cold, dark interiors of clouds. The chemistry of the interstellar medium is extraordinarily complex. Over 200 different molecular species have been detected in interstellar space, including simple sugars, amino acid precursors, and even glycine, one of the simplest amino acids, possibly. The building blocks of life are not confined to planets. They are scattered throughout the interstellar medium of the Milky Way. Let us pause on that for a moment, because it raises a question that may be the most important question we as a species are currently grappling with. If the building blocks of life are spread throughout the galaxy, if the chemistry of life is not unique to Earth but is a natural consequence of the chemistry that plays out in molecular clouds and planetary systems throughout the Milky Way, then why are we not hearing from anyone else? Where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who allegedly asked it at a lunch meeting in 1950. If intelligent life is probable in a galaxy containing hundreds of billions of stars, many with planets, many with the building blocks of life scattered all around, why have we not detected any sign of it? The Fermi paradox is not just a question about extraterrestrial intelligence. It is a question about the Milky Way as a habitat. And there are many proposed answers, most of them deeply unsettling in different ways. Maybe intelligent life is extraordinarily rare, the product of such an improbable chain of events that we are truly alone or nearly alone in the galaxy. Maybe intelligent civilizations tend to destroy themselves before they can become spacefaring. Maybe they become invisible, choosing to minimize their energy output for strategic or ecological reasons. Maybe the universe is young enough that we are among the first intelligent species to arise, cosmic pioneers in an otherwise empty galaxy. Or maybe, and this is one of the more disturbing possibilities, something happens to virtually every advanced civilization at some point in their development, a great filter, some challenge or hazard that almost no one gets through. If the great filter is ahead of us rather than behind us, its implications are catastrophic. These are not idle science fiction speculations. They are serious considerations that emerge directly from what we know about the Milky Way, about its age, its chemistry, its number of potentially habitable worlds, and the absence of any detected signal from another civilization despite decades of searching. The search for extraterrestrial intelligence, SETI, has been running in various forms since Frank Drake pointed a radio telescope at two nearby stars in 1960. More than 60 years of searching, and so far, nothing definitive. The WOW signal in 1977 was a 72-second burst of narrowband radio emission that matched many of the expected characteristics of a signal from space, and it has never been explained and has never been detected again. The Milky Way is silent, as far as we can tell. And that silence is either comforting, we are alone, or terrifying. Something is silencing everyone. Now let us think about the habitability of the Milky Way itself. Not every region of the galaxy is equally hospitable to life. The galactic habitable zone is a concept developed by astrophysicist Guillermo Gonzalez and others, which identifies a ring-shaped region of the Milky Way, roughly between 23,000 and 29,000 light-years from the galactic center, a range that includes our own solar system, as the zone most likely to contain conditions suitable for complex life. Too close to the galactic center, and radiation levels from the dense stellar population and the active galactic nucleus would sterilize planets. Too far from the center, and the interstellar medium lacks the heavier elements, carbon, oxygen, nitrogen, phosphorus, and others, needed to build planets and life, because those elements are produced by multiple generations of stellar nucleosynthesis that have simply not happened yet in the outer galaxy. Our solar system sits at approximately 26,000 light-years from the center, which places us near the inner edge of this proposed habitable zone. This is not a coincidence that many astrobiologists find comfortable to dismiss. The suggestion is that our position in the galaxy, not just in the solar system, but in the galaxy, may be one of the factors that permitted complex life to develop here. We are in a relatively safe, chemically rich region of a relatively calm galaxy, at a time in cosmic history when the galaxy has matured enough to produce the necessary elements, but has not yet reached the end of its star-forming life. The window may be narrow, and we may be sitting in it. There are about 5,000 exoplanets confirmed as of the time this is being written, in just the small volume of the galaxy we have been able to survey. And the data from missions like the Kepler Space Telescope suggests that virtually every star in the Milky Way has planets. The Kepler mission, which monitored approximately 150,000 stars for tiny dips in their brightness caused by planets crossing in front of them, found that small rocky planets, the kind most likely to support life as we know it, are extraordinarily common. Statistical analyses based on Kepler data suggest that there are likely tens of billions of rocky planets in the habitable zones of their host stars in the Milky Way alone. The habitable zone is the range of distances from a star at which liquid water could exist on a planetary surface, and liquid water is considered essential for life as we know it. Tens of billions of potentially habitable rocky worlds in our galaxy alone. But having a rocky planet in a habitable zone is just the beginning. The history of Earth tells us that life can be astonishingly resilient once it gets started, but getting started in the first place, and progressing from simple microbial life to complex multicellular life, to intelligence, to technology, that chain of steps may involve many bottlenecks, many improbable transitions, each of which reduces the number of worlds where the story plays out fully. The evolution of the eukaryotic cell, the type of cell with a nucleus that underlies all complex life on Earth, may have been a singularly improbable event. It appears to have happened only once in the entire history of life on Earth, roughly 2 billion years ago. How many times did it fail to happen on other worlds? We do not know. And that uncertainty is one of the most important uncertainties in science. Let us return to the stars themselves for a moment, because the story of the stars is the story of the Milky Way. Stars come in an extraordinary range of sizes, temperatures, and lifetimes. At one extreme are massive blue stars, O-type stars and B-type stars, blazing with tens of thousands of times the luminosity of the Sun, burning through their fuel in a few million years before exploding as supernovae. They are spectacular but brief. At the other extreme are red dwarf stars, M-type stars, tiny, dim, cool, extraordinarily long-lived. A red dwarf with 1/10 the mass of the Sun burns so slowly that it could live for trillions of years, far longer than the current age of the universe. Red dwarfs are by far the most common type of star in the Milky Way. Roughly 70 to 75% of all stars in the galaxy are red dwarfs. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf. The fact that red dwarfs are so common and so long-lived has profound implications for the question of life in the galaxy. If life can thrive on planets orbiting red dwarfs, and there are significant challenges, including the fact that habitable zone planets around red dwarfs are very close to the star, potentially tidally locked with one hemisphere in permanent day and the other in permanent night, and subject to intense stellar flares, then life could potentially persist in the Milky Way for trillions of years, long after the Sun has died. Our Sun is a G-type star, a yellow dwarf, though its color is actually closer to white. It is roughly average in terms of mass and luminosity compared to all stars in the galaxy, but it is actually more luminous and more massive than most stars, simply because most stars are red dwarfs. The Sun has been burning for about 4.6 billion years and is roughly halfway through its main sequence life. In about 5 billion years, it will exhaust its core hydrogen, expand into a red giant, possibly large enough to engulf the inner planets, possibly including Earth, and then lose its outer layers, leaving behind a white dwarf. The Sun will not explode as a supernova. It is not massive enough. It will die quietly, its outer layers forming a beautiful planetary nebula that will glow for a few thousand years before dispersing into the interstellar medium, and its white dwarf core will slowly cool over billions of years into a black dwarf, a cold, dark stellar remnant. No known black dwarfs yet exist. The universe is not old enough for any white dwarf to have cooled that completely. The Sun is not special in most ways, but it may be special in some. It is what is called a population 1 star, a metal-rich star, meaning it contains significant amounts of elements heavier than hydrogen and helium. This reflects the fact that it was formed from interstellar material that had already been enriched by many previous generations of stars. The chemical richness of the material from which the solar system formed is why the Earth is composed of the diverse array of elements it is, why life could arise here using carbon, nitrogen, oxygen, phosphorus, sulfur, and all the other elements that biology requires. Earlier generations of stars, population 2 stars, which formed in the early Milky Way when the interstellar medium had not yet been enriched by stellar nucleosynthesis, were much poorer in metals, and the planets around them, if any exist, would have had a very different composition. Population 3 stars, the very first stars, formed from pure hydrogen and helium in the universe's infancy, no longer exist, having all lived and died billions of years ago, but they were likely enormous, burning brilliantly and briefly, and seeding the cosmos with the first heavy elements through their supernova deaths. Let us talk about neutron stars and pulsars, because they are among the most extreme objects in the Milky Way, and their properties challenge the imagination in ways that nothing else quite does. When a star with a mass roughly between 8 and 20 times the mass of the Sun exhausts its fuel and collapses, the collapse happens so fast and so violently that the core is compressed to densities unimaginable in ordinary experience. A sphere roughly 20 kilometers across, containing 1 to 3 times the mass of the Sun. At these densities, atoms themselves are crushed out of existence, and the matter is compressed into a sea of neutrons packed together at nuclear density. A teaspoon of neutron star material would weigh about 10 million tons on Earth. The surface gravity of a neutron star is about 200 billion times that of Earth. If you could somehow stand on the surface of a neutron star, which you emphatically could not, you would be crushed to an infinitesimally thin film in the blink of an eye. Neutron stars often spin rapidly when they form, due to the conservation of angular momentum as the core collapses, the same principle that causes a spinning ice skater to spin faster when they pull in their arms. Young pulsars can spin hundreds of times per second, and as they spin, they emit beams of electromagnetic radiation, radio waves, X-rays, gamma rays, from their magnetic poles. If those beams sweep across the Earth as the star rotates, we detect regular pulses of radiation, hence the name pulsar. Pulsars are among the most precise timekeepers in the universe. The millisecond pulsars, the fastest spinning ones, can maintain a rotation rate so stable that they rival atomic clocks in precision. They have been used to test general relativity to extraordinary accuracy and have been proposed as a kind of galactic GPS system for navigating deep space. One of the most dramatic events in the universe involves neutron stars. When 2 neutron stars in a binary system slowly spiral together due to the emission of gravitational waves, literally ripples in the fabric of space-time predicted by Einstein's general relativity, they eventually merge in an event called a kilonova. The gravitational waves emitted by the inspiral of 2 neutron stars were first directly detected on August 17, 2017 by the LIGO and Virgo detectors. in an event designated GW170817. For the first time, astronomers observed both gravitational waves and electromagnetic radiation, a gamma-ray burst and an optical transient, from the same event. The kilonova produced by this merger synthesized enormous quantities of heavy elements, gold, platinum, uranium, and many others, in a flash of our process nucleosynthesis. It is now believed that a significant fraction of all the gold and platinum in the universe was produced in kilonova events. The gold in your jewelry, the platinum in your catalytic converter. These elements were likely forged in the collision of two neutron stars, possibly billions of years before our solar system formed, and then distributed through the interstellar medium, eventually ending up in the molecular cloud that collapsed to form our solar system. Think about that the next time you hold something made of gold. That gold was created in a cosmic catastrophe so violent that it bent space-time as it happened, and the waves from that bending can be detected by instruments sensitive enough to measure a change in length 10,000 times smaller than the width of a proton. The Milky Way is a place where events of that scale happen. Our galaxy has seen millions of neutron star mergers over its history. The gold in this galaxy is the product of stellar violence on a scale that beggars description. The Milky Way also has what are called magnetars, neutron stars with extraordinarily powerful magnetic fields, the most powerful magnetic fields of any known objects in the universe. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's magnetic field. A magnetar's magnetic field can be 1,000 times stronger still, roughly 1 quadrillion times stronger than Earth's magnetic field. A magnetar at the distance of the Moon from Earth would be so magnetically powerful that it would disrupt the iron atoms in our hemoglobin. At the distance of the Sun from Earth, 93 million miles, a magnetar's magnetic field would still be detectable. Magnetars occasionally release sudden, enormous bursts of energy, magnetar flares, caused by shifts in their magnetic fields. On December 27, 2004, a magnetar flare from a magnetar called SGR 1806-20, located about 50,000 light-years away in the Milky Way, briefly ionized the upper atmosphere of Earth and was the brightest event ever observed from outside our solar system. If this magnetar had been within 10 light-years of Earth, the neighborhood of Proxima Centauri, it would have been catastrophic for life on Earth. The Milky Way has harbored explosions of extraordinary violence throughout its history. Supernovae occur in the Milky Way at a rate of roughly 1 to 3 per century. In the historical record, several supernovae have been observed. SN 1006, the brightest supernova in recorded human history, visible in daytime skies for weeks. SN 1054, which produced the Crab Nebula. Tycho's star in 1572, observed by the astronomer Tycho Brahe and so bright it was visible in daylight for 2 weeks. And Kepler's star in 1604, the last supernova in the Milky Way to be observed with the naked eye. The lack of observed supernovae in the Milky Way since 1604 is somewhat surprising given the expected rate. Astronomers believe that several supernovae have occurred in the galaxy since then, but they were hidden behind dense clouds of dust and gas and thus invisible in optical light. They have been detected in other wavelengths, X-ray and radio, after the fact. One star in the Milky Way that astronomers watch closely for a possible imminent supernova is Betelgeuse, the red supergiant in Orion. Betelgeuse is in a late stage of its life. It has exhausted its core hydrogen and helium, is now burning heavier elements, and is expected to explode as a supernova sometime in the next 100,000 years. A cosmically short time, though not particularly imminent on a human timescale. But in late 2019, Betelgeuse dimmed significantly, to about 60% of its typical brightness, sparking widespread excitement and speculation. Could this be the precursor to a supernova? Astronomers eventually determined that the Great Dimming, as it became known, was caused by a large eruption of stellar material that cooled and condensed into dust, temporarily obscuring the star. But the event highlighted just how closely watched this star is. When Betelgeuse does explode, and it will be visible in daylight for weeks or months, and it will briefly be the brightest object in the night sky other than the moon. It will be a historical spectacle unlike anything seen by humans since 1006. At 700 light-years away, it poses no threat to life on Earth. A closer supernova, however, could be a different story. A supernova within about 25 to 50 light-years of Earth could pose a serious threat, potentially stripping the ozone layer and exposing the surface to intense ultraviolet radiation. Some researchers have proposed that one or more nearby supernovae in the past may have contributed to mass extinction events on Earth. There is evidence, in the form of enriched concentrations of the radioactive isotope iron-60 in deep-sea sediments, of a supernova explosion that occurred within about 300 light-years of Earth about 2 to 3 million years ago, roughly coinciding with the early Pleistocene, a period of significant climate change and the rise of the Homo genus. Whether this supernova had any direct effect on the course of human evolution is speculative, but the proximity is intriguing. The Milky Way, even in its relatively calm state, is not entirely safe. We are part of a violent galaxy, and the evidence of its violence occasionally reaches our doorstep. Now let us explore the concept of stellar populations and stellar generations in more depth, because this is where the biography of the Milky Way connects directly to the biography of every atom in your body. Stars are the universe's element factories. Hydrogen and helium were produced in the Big Bang, but virtually every other element on the periodic table was made in stars. Carbon, oxygen, nitrogen, the essential elements of life, are made by nuclear fusion in the cores of stars. Silicon, sulfur, calcium, iron, the elements of the Earth's interior and crust, are made in the cores of massive stars and distributed by their supernovae. Gold, platinum, uranium, and the heavy transuranics are made in neutron star mergers and in the supernovae of the most massive stars. The Milky Way has been performing this chemical enrichment process for 13.6 billion years, and with each generation of stars that forms and dies, the interstellar medium becomes richer in heavy elements, more chemically complex, more capable of producing the diverse materials needed for rocky planets and biology. The first generation of stars, population 3, formed from pure hydrogen and helium. They were likely extremely massive, living only a few million years before exploding as supernovae and enriching the surrounding medium with the first heavy elements. The second generation, population 2, formed from slightly enriched material and are still found today as ancient stars in globular clusters and the galactic halo, dim, old, metal-poor relics of the early Milky Way. The most ancient stars in the Milky Way are found in the halo, and the oldest confirmed stellar object is Methuselah's star, formerly designated HD 140283, which has been calculated to be approximately 14.5 billion years old, which, notably, is older than the current best estimate for the age of the universe, a discrepancy that has puzzled astronomers and likely reflects uncertainties in the age measurement. Subsequent analysis has revised the age estimate downward somewhat, to about 13.7 plus or minus 700 million years, which is consistent with the universe's age within uncertainties. But the closeness of this star's age to the age of the universe underscores just how ancient the oldest stars in the Milky Way are. Population 1 stars, like our Sun, formed from material already enriched by multiple generations of stellar nucleosynthesis. The Sun contains about 2% by mass of elements heavier than helium. Astronomers call all of these metals, confusingly, even elements like carbon and oxygen. This 2% is the product of billions of years of stellar nucleosynthesis in earlier generations of stars. The fact that you exist, that you are made of carbon, nitrogen, oxygen, phosphorus, iron, calcium, and dozens of other elements, is the direct result of the Milky Way's long history of stellar birth and death. You are not just living in the Milky Way. You are a product of it. Your atoms are the Milky Way's atoms. Your existence is an expression of the galaxy's chemistry. Carl Sagan said it most beautifully. We are made of star stuff. But perhaps even more accurate would be to say we are made of Milky Way stuff. The particular history of this particular galaxy, its mergers, its star formation history, its chemical evolution, produced the specific mix of elements in the specific proportions that made our solar system, our planet, and our bodies possible. A galaxy with a different history might have produced different elements in different proportions, and the life that arose in it, if any, might be unrecognizably different. Let us talk about cosmic rays, because they are one of the Milky Way's most energetic and least understood exports. Cosmic rays are high-energy particles, mostly protons, but also heavier atomic nuclei and electrons, that stream through the galaxy at nearly the speed of light, carrying energies that can exceed any particle produced by human-made accelerators by many orders of magnitude. The most energetic cosmic rays carry an energy equivalent to a baseball pitched at about 100 kilometers per hour, all packed into a single subatomic particle. They come from a variety of sources. Supernova remnants are believed to be the major source of cosmic rays up to a certain energy, with more energetic ones possibly originating from more extreme sources like magnetars, active galactic nuclei, and gamma-ray bursts. Cosmic rays fill the Milky Way, spiraling along magnetic field lines, occasionally interacting with interstellar gas to produce secondary particles and gamma rays. When they hit Earth's atmosphere, they create showers of secondary particles, muons, pions, electrons, photons, that rain down on the surface. Right now, several cosmic ray muons are passing through your body every second. You are being continuously penetrated by particles from some of the most energetic events in the galaxy, and you will never feel any of them. Cosmic rays are also thought to play a role in cloud formation in Earth's atmosphere, with some researchers proposing that galactic cosmic ray flux influences climate over long timescales. During periods when the solar system passes through a spiral arm, where cosmic ray flux is higher due to the higher density of supernova remnants, the flux of cosmic rays reaching Earth may increase, potentially affecting cloud cover and climate. This idea is controversial and the subject of ongoing research, but it illustrates how intimately the Earth's environment may be connected to the larger structure and activity of the Milky Way. Now let us turn our attention to gamma-ray bursts, because they represent the most violent explosions in the known universe, and the Milky Way has experienced them. Gamma-ray bursts are extremely energetic explosions observed in distant galaxies, releasing in seconds the equivalent of the Sun's total energy output over its entire 10 billion-year lifetime. They come in two varieties: short gamma-ray bursts, lasting less than 2 seconds and produced by neutron star mergers, like the kilonova event GW 170817, and long gamma-ray bursts, lasting more than 2 seconds and produced by the collapse of extremely massive, rapidly rotating stars, hypernovae. A long gamma-ray burst from within the Milky Way, if its jet happened to be pointed toward Earth, could be catastrophic. A burst within a few thousand light-years of Earth could strip the ozone layer and potentially trigger a mass extinction. Some researchers have proposed that the Ordovician mass extinction, approximately 440 million years ago, may have been triggered or contributed to by a nearby gamma-ray burst, though this remains speculative. The good news is that long gamma-ray bursts are more common in metal-poor galaxies than in metal-rich ones like the modern Milky Way. As the Milky Way has aged and its stars have become progressively more metal-rich, the rate of long gamma-ray bursts within it has likely decreased. The early Milky Way, more metal-poor, may have been a more dangerous place for life in this respect. The current Milky Way, calmer in this regard, may represent a cosmic window during which life is less likely to be sterilized by such extreme events. Again, the timing of our existence within the galaxy's history may not be entirely coincidental. It is time to talk about a stunning recent discovery that has changed our understanding of the Milky Way's recent history. In 2020, astronomers announced the discovery of what are called the Fermi bubbles, or more specifically, a related but distinct structure that had been detected by the Rosetta X-ray telescope. But let us start with the Fermi bubbles themselves. In 2010, scientists using the Fermi Gamma-ray Space Telescope discovered two enormous bubbles of plasma extending above and below the galactic plane, each roughly 25,000 light-years tall, centered on the galactic center. These Fermi bubbles are thought to be the result of some enormous outburst of energy from the galactic center, possibly from a period of intense activity of Sagittarius A star, perhaps a few million years ago when the black hole was actively consuming gas at a higher rate than today, producing powerful jets that inflated these structures. The energy involved is staggering. Roughly 100,000 supernovae worth of energy was needed to inflate them. Then, in 2020, the Rosetta All-Sky Survey revealed even larger structures, the Rosetta bubbles. which extend about 45,000 light-years above and below the galactic plane, engulfing the Fermi bubbles. The Rosetta bubbles are even more energetic, requiring an energy input equivalent to perhaps a million supernovae over the course of some millions of years. Together, these structures paint a picture of a galactic center that was far more active in the relatively recent past. Active in a way that would have been significant on galactic scales, though probably not catastrophic for life on Earth given the distance. But the implication is clear. Sagittarius A star is not always the quiet, sleeping giant it is today. It wakes up, and when it does, it exhales on a scale that reshapes the galaxy. Let us now explore the concept of stars that should not exist. The Milky Way contains a population of young, hot stars in its innermost region, within just a few light-years of Sagittarius A star, that astronomers have called the S-stars. These stars are a deep puzzle. Young stars should not be able to form so close to a supermassive black hole. The tidal forces near the black hole are so extreme that they should tear apart any molecular cloud before it can collapse to form stars. And yet there they are, young, massive, hot stars, some of them on tight orbits around Sagittarius A star, completing their orbits in just a few years. How did they get there? One hypothesis is that they formed in a dense molecular cloud farther from the center and then migrated inward over time through a process called orbital decay. Another is that they are the remnants of a dissolved star cluster that was dragged toward the center by dynamical friction. A third, more exotic possibility is that they somehow formed in situ, in conditions that we do not yet understand. The S-stars are one of the many mysteries of the galactic center, a region where the physics we think we understand seems to strain and buckle under the extremity of the conditions. The most famous of the S-stars is S2, which has been monitored continuously for over 25 years by teams at the European Southern Observatory. In 2018, S2 made its closest approach to Sagittarius A star, coming within just 120 astronomical units of the black hole, about 3 times the distance from the Sun to Neptune, while moving at about 2.7% of the speed of light. This periapsis passage allowed astronomers to test Einstein's general relativity in the extreme gravitational field of a supermassive black hole. The orbit of S2 showed a relativistic precession, a rotation of the orbital ellipse predicted by general relativity, confirming Einstein's theory to extraordinary precision in one of the most extreme gravitational environments accessible to observation. The team involved, led by Reinhard Genzel and Andrea Ghez, was awarded the Nobel Prize in Physics in 2020, shared with Roger Penrose, for the discovery of a compact object, Sagittarius A star, at the center of our galaxy, and the decades of observations that established its nature as a supermassive black hole. Here is something that will genuinely reframe how you think about the Milky Way's appearance. From inside the galaxy, looking toward the galactic center in the direction of Sagittarius, the densest part of the Milky Way is in that direction, with stars packed more tightly and the band of the Milky Way at its widest. But from another galaxy, or from outside our galaxy looking in, the Milky Way would look very different from different directions. Face on, it would show the full grandeur of the spiral arms, the central bar, the nucleus. Edge on, it would appear as a thin disk with a central bulge. We have never seen the Milky Way from outside. We have only indirect knowledge of its structure, pieced together from maps made by radio telescopes, infrared telescopes, and the extraordinary stellar motion data from Gaia. Every image you have ever seen of a beautiful face-on spiral galaxy described as resembling the Milky Way, Messier 74, Messier 101, NGC 6744, is an illustration by analogy, not a photograph of our own galaxy. We are guessing at our own face by looking at other people's photographs. The Gaia spacecraft, launched in 2013 by the European Space Agency, has been one of the most transformative instruments in the history of astronomy. It has measured the positions, distances, and motions of approximately 2 billion stars in the Milky Way with unprecedented precision. The data from Gaia has revealed that the Milky Way is far more dynamic and complex than previously thought. It has revealed stellar streams from disrupted dwarf galaxies and globular clusters, mapped the warp and corrugation of the disk, identified stars moving at hypersonic velocities on their way out of the galaxy, revealed the ancient Gaian-Enceladus merger, and shown that the galactic disk is not a smooth, regular structure but is rippled and disturbed, possibly from the passage of the Sagittarius dwarf galaxy through the disk in the recent past. One of the most dramatic discoveries enabled by Gaia is the detection of hypervelocity stars. Stars moving through the Milky Way at such extreme velocities that they are unbound from the galaxy's gravity and will eventually escape into intergalactic space. These stars have been accelerated to extraordinary velocities, some reaching over 1,000 kilometers per second, by a gravitational slingshot interaction near the supermassive black hole at the galactic center. The mechanism is called the Hills mechanism, after astronomer Jack Hills, who predicted it in 1988. A binary star system ventures too close to Sagittarius A star. The black hole's tidal forces disrupt the binary, capturing one star into a tight orbit around the black hole and flinging the other outward at enormous velocity. The ejected star becomes a hypervelocity star, departing the galactic center at speeds high enough to escape the Milky Way entirely over the course of several 100 million years. These are the galaxy's exiles, flung out into the lonely void of intergalactic space by the gravitational violence at the galaxy's heart. Now, it is time to address a speculation that has captured the imagination of many astronomers and exobiologists. What if the Milky Way itself has, or had, something like an immune system? This is not as absurd as it sounds. Some theorists have proposed a concept called the rare Earth hypothesis, which suggests that the conditions for complex intelligent life are so stringent, requiring a galactic habitable zone, a right type of star, a right type of planetary system, a right period of galactic history, that complex life is exceedingly rare. But others have proposed something even more provocative: the hypothesis that the galaxy might have been seeded with life by an early civilization, either accidentally through panspermia, the transport of life via comets and asteroids, or deliberately. This is the concept of directed panspermia, proposed seriously by Francis Crick, one of the discoverers of the structure of DNA, who suggested in the 1970s that life on Earth might have been deliberately seeded by an extraterrestrial civilization. While this idea is not mainstream, it raises interesting questions about the origin of life and the potential interconnectedness of life in the galaxy. Panspermia in general, the idea that life or its precursors can travel between star systems on interstellar objects, received a boost from the discovery of the first known interstellar object to pass through our solar system, Oumuamua, detected in 2017. Oumuamua was remarkable in several ways. Its elongated shape, its anomalous acceleration, and its high velocity all set it apart from normal solar system objects. Most scientists interpret it as a natural object, possibly a fragment of an exoplanet or a nitrogen iceberg. But its passage through our solar system was a demonstration that objects do travel between star systems, and that the interstellar medium is not as isolated as one might think. If even simple organic molecules can survive the journey between stars, protected inside rocks or ices, the question of whether life itself could make such a journey becomes less far-fetched. The galaxy's history is also written in its chemical abundance patterns, a field called galactic chemical evolution. By studying the composition of stars of different ages, using spectroscopy to analyze the wavelengths of light they emit and absorb, astronomers can trace how the abundance of different elements in the Milky Way has changed over time. In the early Milky Way, the interstellar medium was almost entirely hydrogen and helium, with trace amounts of lithium. With each generation of stars, elements like carbon, oxygen, and nitrogen were added in increasing quantities. Iron and other iron peak elements grew in abundance more slowly, primarily produced in type Ia supernovae, the thermonuclear explosions of white dwarf stars and binary systems, which occur on longer timescales than the core collapse supernovae that produce elements like oxygen and neon. By measuring the ratio of iron to oxygen in stars of different ages, astronomers can reconstruct the star formation history of the Milky Way, tracking periods of rapid star formation and quiescence. The Milky Way's chemical history is written in its stars, and we are learning to read it. One of the strangest features of the Milky Way is something called the galactic bar. The Milky Way is classified as a barred spiral galaxy, SBBC in the Hubble classification scheme, because it has a central bar-shaped structure of stars connecting the innermost ends of the spiral arms. The bar extends roughly 27,000 light-years from end to end, oriented at an angle of roughly 44 degrees to the line connecting our Sun to the galactic center. It is composed of old, red, and yellow stars, and it plays a crucial role in the dynamics of the inner galaxy, channeling gas toward the center and fueling star formation in the central molecular zone, the densely packed region of gas and dust immediately surrounding Sagittarius A star. The bar itself is rotating, slower than the spiral arms and the disk stars, and its interaction with the rest of the galaxy drives complex dynamical resonances that affect the orbits of stars throughout the inner galaxy. The galactic bulge, the central, roughly spherical concentration of stars at the center of the Milky Way, is a mixture of the bar and a true spheroidal bulge, with a complex stellar population that includes both old, metal-poor stars similar to those in globular clusters and younger, metal-rich stars that formed more recently. Understanding the structure and origin of the bulge is one of the active frontiers of Milky Way research, with data from Gaia, the VISTA variables in the Via Lactea survey, the Apogee spectroscopic survey, and other programs steadily building a more detailed picture of this central region. There is a population of stars in the Milky Way called high-velocity stars or runaway stars, not as extreme as hypervelocity stars, but moving significantly faster than the typical stellar population. Some of these are produced by the same Hill's mechanism, but others are the result of supernova explosions in binary star systems. When one star in a binary system explodes as a supernova, if the explosion is asymmetric, if the stellar remnant receives a natal kick in a particular direction, the binary system can be disrupted, and the surviving companion star is released at high velocity, moving through the galaxy on an unusual orbit. Pulsar surveys have detected many young neutron stars with high velocities, natal kicks of hundreds of kilometers per second from the supernova explosion, confirming that this process happens regularly. These runaway stars and neutron stars carry the memory of their violent birth in their trajectories, little cannonballs fired by supernovae across the galaxy. Let us now take a moment to consider what we know about the future of the Milky Way, and not just the Andromeda collision we have already discussed. The long-term future of the galaxy is a fascinating and somewhat melancholy topic. In the current universe, the Milky Way is forming stars at a rate of roughly 1 to 3 solar masses per year, fairly moderate by galactic standards. But the gas supply for star formation is finite. Galaxies like the Milky Way are thought to be in the process of gradually transitioning from star-forming blue galaxies to quiescent red galaxies, as their interstellar gas is used up or expelled. The Milky Way is currently considered a transitional case, still forming stars but less actively than spiral galaxies like the Whirlpool Galaxy or the Sombrero Galaxy. In billions of years, the gas will be exhausted, star formation will cease, and the galaxy will become dominated by aging, redder stars and the white dwarfs and neutron stars that remain from earlier generations. The Milky merger with Andromeda will trigger a brief burst of intense star formation, the gas from both galaxies compressed and heated by the collision, producing a wave of new stars, but this too will eventually exhaust the available fuel. On even longer timescales, the future is darker. Over hundreds of billions of years, stars will continue to die. The most massive stars went long ago. Over the next tens of billions of years, the sun-like stars will die. In hundreds of billions of years, even the longest-lived red dwarfs will fade. In 10 to the 14 years, 100 trillion years, the last stars will flicker out, and the galaxy will be a graveyard of white dwarfs slowly cooling to black, neutron stars, and black holes, held together in their orbits by gravity, the galaxy structure intact but dark and cold. This epoch is sometimes called the degenerate era. Over even longer timescales, 10 to the 37 to 10 to the 40 years, even the matter in white dwarfs and neutron stars may disintegrate if proton decay occurs at the rate predicted by some grand unified theories. And the black holes, including Sagittarius A star, will eventually evaporate through Hawking radiation over timescales of 10 to the 67 years for a stellar mass black hole and something like 10 to the 97 years for Sagittarius A star. The Milky Way will end not with a bang, but with an almost imperceptibly slow, cold fade to nothing. But that is so far in the future that it is essentially meaningless on any human timescale. On the timescales relevant to us, millions of years, tens of millions of years, the Milky Way will look broadly similar to how it looks today, continuing its slow cannibalism of satellite galaxies, gradually consuming its gas in new star formation, and drifting toward the Andromeda collision. Let us now explore something that exists at the intersection of the scientific and the almost philosophical: the Milky Way's place in the cosmic web. The universe, on the largest scales, is not uniformly distributed. Galaxies are not scattered randomly, but are organized into a vast, three-dimensional network of filaments, sheets, and nodes, a cosmic web, or large-scale structure of the universe. Galaxies and galaxy clusters are concentrated along the filaments and at the nodes where filaments intersect, while vast regions called voids, nearly empty bubbles of space, sometimes hundreds of millions of light-years across, lie between the filaments. The Milky Way sits in the local group, which sits in the Virgo supercluster, which is itself a component of the Laniakea supercluster. Laniakea is a component of a larger structure called the Perseus-Pisces supercluster Laniakea network, one of the major filaments of the cosmic web. Our galaxy is not in a void. It is near the edge of a void, embedded in a filament, part of a local overdensity that includes several major galaxy clusters. The Boötes void, one of the largest known voids in the universe, is a roughly spherical region about 330 million light-years in diameter, located about 700 million light-years from Earth. It contains almost no galaxies. Just 60 galaxies have been found inside it, where you would expect something like 2,000 based on the average galaxy density of the universe. The void is so enormous and so empty that if the Milky Way were inside it, the nearest galaxy outside it would be hundreds of millions of light-years away, and the night sky would be almost completely dark even with a powerful telescope. Our position near a filament, with a rich surrounding of galaxies, is one of the factors that has shaped the Milky Way's history, through mergers, gravitational interactions, and the availability of infalling gas. The local group itself is falling toward the Virgo cluster, the nearest major galaxy cluster, about 54 million light-years away, containing somewhere between 1,000 and 2,000 galaxies and having a total mass of about 1 quadrillion solar masses. The gravitational pull of the Virgo cluster on the local group produces what is called the Virgocentric flow, a component of our motion through space that adds to the overall motion toward the great attractor. We are being pulled in multiple directions by multiple gravitational attractors simultaneously, and our resulting trajectory through the universe is the complex sum of all these influences. Now, a question that may have been nagging you, perhaps since the very beginning. Given everything we have discussed, the size of the Milky Way, its age, its number of stars, the fact that planetary systems are common, that the building blocks of life are widespread, that the galaxy has been around for almost 13.5 billion years, why does it feel so isolated? Why does space feel so empty? Why, when you look up at the sky, do you see stars but not the ships of other civilizations, not the directed beams of their communications, not the Dyson spheres dimming their stars as they harvest stellar energy? The answer may simply be that the universe is larger and emptier than our intuitions can handle. Even the Milky Way, with 400 billion stars, is mostly empty space, and civilizations, if they exist, need not be broadcasting in ways we can detect, or their broadcasts may have already passed us by unnoticed, or they may be communicating on wavelengths or by methods we have not yet imagined. The absence of evidence is not evidence of absence, as the saying goes. But it is a real and profound puzzle. The Milky Way has had over 13 billion years to produce intelligent life and for that life to spread, communicate, or make its presence known. In that time, on a cosmic scale, an advanced civilization could theoretically colonize the entire galaxy in just a few tens of millions of years, even with travel speeds far below the speed of light. The fact that we detect no such galaxy-wide presence is one of the most fundamental mysteries of our time. Some researchers take the Fermi paradox as evidence that we are truly rare, that the emergence of intelligent, technological civilization is not a natural outcome of the galaxy's chemistry and history, but an extraordinary fluke, a once-in-a-galaxy event, or perhaps once in a universe. Others take it as evidence that something happens, a great filter, that prevents civilizations from reaching the stage of galaxy-wide presence. And others suggest that the galaxy is teeming with life, but that life, for the most part, is microbial and uninterested in broadcasting its existence. The truth is that we do not know. And that uncertainty, that profound, galaxy-spanning uncertainty, is itself one of the most important facts about the Milky Way. Here is something that almost no one who has not studied astronomy is aware of, and it should genuinely astonish you. The Milky Way is accelerating away from many other galaxies. Or rather, those galaxies are accelerating away from us, because of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Right now, all galaxies beyond a certain distance, called the Hubble volume or the observable universe, are moving away from us faster than the speed of light, due to the expansion of space itself, and are already beyond our ability to ever reach or communicate with, no matter how advanced our technology becomes. The universe is expanding so fast that the vast majority of it is already forever beyond our reach. And this expansion is accelerating. In the distant future, even the galaxies that are currently within our observable universe will be swept beyond the horizon of reachability, one by one. Eventually, in hundreds of billions of years, the Milky Way and its gravitationally bound companions will be alone, an island in an otherwise dark, empty, expanding void. The rest of the universe will have disappeared beyond the cosmic horizon, unreachable, undetectable. We will be cosmically isolated in a way that makes our current isolation seem like a neighborhood gathering. This prospect, sometimes called the Big Freeze or heat death scenario, if the universe continues to expand indefinitely with increasing acceleration, is the long-term extrapolation of cosmology as currently understood, though it depends on the exact nature of dark energy remaining constant. If dark energy changes over time, different futures are possible. But as things currently stand, the universe is on a trajectory toward a cold, dark, empty, maximally entropic state, and the Milky Way will be one of the last holdouts, a small island of organized structure in an otherwise structureless void. Now let us explore the idea that the Milky Way might have a pulse. Not literally, but metaphorically, cyclical variations in its activity, its star formation rate, and even its potential impact on life within it. There is evidence that the rate of star formation in the Milky Way has not been constant over its history. There appear to have been bursts of intense star formation separated by quieter periods. Some researchers have proposed that the passages of the solar system through the spiral arms of the galaxy, which happens roughly every 100 million years or so as the sun's orbit brings it through a denser region, might be associated with increased cosmic ray flux, increased supernova rates, and possibly climate changes on Earth. There is a controversial but persistent correlation between the timing of these arm crossings and the timing of glaciation periods and some mass extinction events on Earth, though establishing causation rather than mere correlation is extraordinarily difficult. The idea that the Milky Way's large-scale structure and history could influence the fate of life on individual planets within it is, on one level, deeply unsettling. It suggests that life on Earth is not just subject to local hazards, asteroid impacts, volcanic eruptions, solar variability, but is also subject to the behavior of the galaxy as a whole. That the rhythm of the Milky Way, the rotation of its spiral arms, the activity of its central black hole, the passage of satellite galaxies, may have shaped the history of life on Earth in ways we are only beginning to appreciate. There is one more aspect of the Milky Way that deserves extended discussion, because it is perhaps the most profound and the least appreciated. The question of what the Milky Way means. Not in a scientific sense, but in a human sense. For almost all of human history, people have looked up at the Milky Way without knowing what it was. In ancient times, it was interpreted through the lens of mythology and cosmology in every culture on Earth. The ancient Greeks called it the Milky Circle, and one of their myths said it was formed when the goddess Hera spilled her milk while nursing the infant Heracles. The Milky Way was sometimes called the River of Heaven, the Road of Souls, the Path of the White Elephant, the River of Stars. In Native American traditions, it was the Path of Ghosts, the road taken by the souls of the dead. In Hindu cosmology, it was a reflection of the Ganges River in heaven. In Norse mythology, it was the bridge Bifrost, connecting the human world to the realm of the gods. Across human cultures, in every corner of the world, the Milky Way was recognized as something extraordinary, something that demanded explanation, something that spoke to the deepest questions of existence. And then came Galileo in 1610, who pointed his telescope at the Milky Way and made a discovery that changed everything. The diffuse light of the Milky Way, he found, was composed of countless individual stars, too faint and numerous to be resolved by the naked eye. In his book Sidereus Nuncius, The Starry Messenger, he wrote that the Milky Way is nothing but a mass of innumerable stars planted together in clusters. With those words, the Milky Way stopped being a mythological object and became an astronomical one. But the full scope of what it was, a galaxy, one of billions, 200,000 light-years across and containing hundreds of billions of stars, was not understood until the 20th century. The key figure in that revolution was Edwin Hubble, who in 1924 used Cepheid variable stars as distance indicators to determine that the Andromeda Nebula, as it was then called, was too far away to be part of the Milky Way. It was an island universe, a separate, distinct galaxy at an enormous distance. This single discovery transformed our understanding of the cosmos overnight. The Milky Way was not the universe. It was not even the whole of the local universe. It was one galaxy among many, among what turned out to be billions. The scale of the cosmos expanded by a factor of millions in a single observational revelation. But even before Hubble, the astronomer Harlow Shapley had, in 1918, used globular clusters to determine the approximate size and shape of the Milky Way and the position of the Sun within it. Shapley found that the globular clusters were not distributed uniformly around the sky, but were concentrated toward the constellation Sagittarius, indicating that the center of the galaxy lay in that direction and that the Sun was far from the center, roughly 26,000 light-years away from it. This was the first clear demonstration that the Sun was not at the center of the Milky Way, and it echoed the Copernican revolution of 3 centuries earlier, which had displaced the Earth from the center of the solar system. We were not at the center of the solar system. We were not at the center of the Milky Way. We were not even in a prominent position within the galaxy. We were in the suburbs, orbiting an unremarkable star in a minor spiral arm of an average-sized galaxy in a small group of galaxies in one corner of an incomprehensibly vast universe. This progressive displacement from centrality is one of the most important intellectual journeys humanity has undertaken, and the Milky Way is central to that story. Each expansion of our cosmic horizon has come with a diminishment of our sense of cosmic centrality and, for some, a corresponding expansion of wonder. The Milky Way is both the instrument and the subject of this journey. Here is a final thought about what the Milky Way reveals about the nature of existence. The galaxy contains, as we have established, hundreds of billions of stars. Most of those stars have planets. Many of those planets are in the habitable zones of their stars. The building blocks of life are scattered everywhere. The galaxy has been around for 13 billion years. And as far as we can currently tell, we are the only beings in this galaxy who have looked up and wondered about their place in it, who have built telescopes and spacecraft and mathematics and physics to understand it, who have been moved to awe and terror and joy by the sight of it. Whether we are truly alone or whether there are others out there we have not yet found, the fact that this astonishment, this capacity to look at the Milky Way and feel its scale and wonder, exists at all is one of the most extraordinary facts about the galaxy. The universe has, through 14 billion years of evolution, through the birth and death of countless stars, through the slow chemical enrichment of the interstellar medium, through the formation of rocky planets and the emergence of life and the long climb of evolution, produced creatures who can look at the galaxy and say, "I understand what I'm looking at, and it is extraordinary." And that, perhaps, is the most extraordinary fact of all. Let us now return to some of the individual wonders within the Milky Way that we have touched on and some we have not yet reached, because this galaxy is so extraordinarily rich that there is always more to say. Let us start with the molecular cloud nurseries that serve as the cradles of stellar birth, particularly the giant molecular clouds, the largest discrete objects in the Milky Way. These are enormous concentrations of cold, dense gas, primarily molecular hydrogen, that can contain up to 10 million solar masses of material, span hundreds of light years, and persist for tens of millions of years. They are the reservoirs from which new stars form. The Milky Way contains on the order of several thousand giant molecular clouds, mostly concentrated in the spiral arms. Some of the most famous and most studied are in the constellations Cygnus, Carina, Sagittarius, and Ophiuchus. Within these clouds, pockets of particularly dense gas collapse under their own gravity, fragments spinning as they collapse, heating up at their centers, and eventually igniting nuclear fusion to become new stars. The process of star formation is not smooth or uniform. It is violent, turbulent, and chaotic, driven by a complex interplay of gravity, turbulence, magnetic fields, and the feedback from newly forming stars themselves. One of the most intriguing recent discoveries in the Milky Way is Maggie, a giant gas filament discovered in 2021 using data from the Hi-4Pi survey. Maggie is a structure of atomic hydrogen gas roughly 3,900 light-years long and 130 light-years wide, located on the far side of the Milky Way from our perspective, about 55,000 light-years from the galactic center. It is one of the longest known coherent gas structures in the galaxy. What makes Maggie significant is that it appears to be a collector, a structure where gas from a large volume is slowly draining into a filament before being channeled into star-forming regions. It represents a previously unappreciated step in the life cycle of interstellar gas, a vast funnel collecting raw material from the surrounding galaxy for future star formation. The life cycle of matter in the Milky Way is a cycle in the truest sense. Gas condenses from the diffuse interstellar medium into molecular clouds. Within molecular clouds, dense cores collapse to form stars. Stars process hydrogen and helium into heavier elements through nuclear fusion. When stars die, gently, as planetary nebulae, or violently, as supernovae, they return their processed material to the interstellar medium, enriching it with heavy elements. This enriched material eventually finds its way back into new molecular clouds, where it contributes to the formation of new stars and planetary systems. The atoms in your body have gone through this cycle multiple times in the history of the Milky Way. The carbon in your DNA was probably processed through at least 1 or 2 generations of stars before being incorporated into the molecular cloud that formed our solar system. You are not just made of the Milky Way. You are a chapter in the Milky Way's ongoing story. There is a region of the Milky Way that astronomers call the central molecular zone, a concentration of dense molecular gas in the innermost 300 light-years of the galaxy, surrounding Sagittarius A star. The central molecular zone contains several percent of all the molecular gas in the entire Milky Way, packed into an area a tiny fraction of the galaxy's total size. It is one of the most complex and extreme environments in the galaxy. High gas temperatures, high cosmic ray ionization rates due to the proximity to the galactic center, intense magnetic fields, powerful tidal forces from Sagittarius A star, and a complex chemistry involving molecules as complicated as alcohols, glycols, and amino acid precursors. The central molecular zone has a very different star formation efficiency from the rest of the galaxy. Despite containing enormous amounts of gas, it forms far fewer stars per unit mass of gas than the outer disk, a puzzle known as the star formation deficit in the central molecular zone. Understanding why requires grappling with the complex physics of this region, where the simple models that work well in the outer disk break down. One of the remarkable star clusters in the central molecular zone is the Arches cluster, one of the densest and most massive young star clusters in the entire Milky Way, containing over 100 O-type stars, the most massive, brightest, and shortest-lived class of stars, within a region just 1 light-year across. It is so extreme that stars in its core are separated by only about 100 AU, roughly the distance from the Sun to the Kuiper Belt. The Arches cluster is thought to be only about 2 million years old, an infant in cosmic terms, and is already being disrupted by the tidal forces of the galactic center. It will likely dissipate within the next few tens of millions of years, its stars dispersed into the general stellar population of the galactic center. Another extraordinary cluster nearby is the quintuplet cluster, named after 5 bright stars in its center that stood out in early infrared images. The quintuplet cluster contains the Pistol star, one of the most luminous known stars in the Milky Way, emitting about 10 million times the luminosity of the Sun. The Pistol star is a luminous blue variable, an unstable, extremely massive star prone to periodic outbursts, losing mass at a prodigious rate and surrounded by a nebula of ejected material. At its distance of about 25,000 light-years, it is invisible to the naked eye, hidden behind the dust of the galactic center. But at an equivalent distance of 100 light-years, it would outshine Venus. Now let us talk about a concept called stellar archaeology, or near-field cosmology. Because hidden within the Milky Way, in its halo stars, its oldest star clusters, its most metal-poor stellar populations, is a record of the universe's earliest epochs. The stars in the halo, many of them billions of years old and enriched with only traces of heavy elements, formed in the very early universe, in proto-galactic fragments and dwarf galaxies that later merged to form the Milky Way. By studying their chemical compositions in detail, measuring the abundances of dozens of elements using high-resolution spectroscopy, astronomers can reconstruct the conditions in the early universe, the nature of the first supernovae, the rate of neutron star mergers, the earliest phases of chemical enrichment. The Milky Way is, in this sense, a time machine. The galaxy's oldest stars preserve information about the universe's infancy that cannot be obtained in any other way. A particularly important class of ancient stars are called carbon-enhanced metal-poor stars, or CEMP stars, which are metal-poor stars with unusually high carbon abundances. They are thought to be the descendants of the first generation of massive stars, population 3 stars, whose supernovae produced carbon-rich, iron-poor yields quite different from the supernovae of later generations. By studying CEMP stars, astronomers can infer the properties of population 3 stars, which can never be directly observed since they lived and died in the universe's first billion years. The oldest and most metal-poor stars in the Milky Way's halo are thus archaeological artifacts, fossils of a cosmic era that ended before the Earth was born. Something that deserves mention here is the extraordinary technological achievement that has allowed us to study the Milky Way in such detail. We have gone from Galileo's telescope in 1610, which could barely resolve individual stars in the Milky Way's outer regions, to Gaia in the 21st century, mapping nearly 2 billion stars with sub-micro-arcsecond precision. We have gone from optical telescopes, sensitive only to visible light, to radio telescopes, infrared telescopes, X-ray space observatories, gamma-ray telescopes, and now gravitational wave detectors, each opening a new window on the galaxy and revealing structures and phenomena completely invisible in other wavelengths. The Milky Way we see in visible light is just one face of the galaxy. In radio waves, we see the hydrogen gas of the interstellar medium, tracing the spiral arms and the dynamics of the disk. In infrared, we see through the dust that obscures the galactic center and the distant disk, revealing the stars and structures hidden behind it. In X-rays, we see the hot plasma of supernova remnants, the accretion disks around compact objects, the flickering activity of Sagittarius A star. In gamma rays, we see the Fermi bubbles and the glow of cosmic ray interactions. The Milky Way is a multi-wavelength spectacle, each wavelength band telling a different part of the story. The Atacama Large Millimeter Array, or ALMA, in Chile, is among the most powerful of the current generation of observatories for studying the Milky Way. Its extraordinary resolution at millimeter and sub-millimeter wavelengths allows it to peer deep into molecular clouds to study the earliest stages of star formation, to map the chemistry of the interstellar medium in extraordinary detail, and to observe the motion of gas in the vicinity of Sagittarius A star. When the Event Horizon Telescope imaged Sagittarius A star in 2022, ALMA was one of the 8 radio observatories around the world whose data were combined to produce that image. The image was assembled from petabytes of data recorded on physical hard drives flown by airplane from observatories on multiple continents, then combined using a technique called very long baseline interferometry to create a virtual telescope with a diameter of the entire Earth. Think about what that means. To see the shadow of the black hole at the center of the Milky Way, 26,000 light-years away, in a structure only 24 million kilometers across, humans had to build a telescope the size of the Earth. The scale of the challenge mirrors the scale of the object being observed. Let us now spend a moment on what might be the strangest known population of objects in the Milky Way, the Thorne-Zitko objects. These are theoretical, and possibly real, hybrid stars that consist of a neutron star embedded in the core of a red giant or supergiant. They were predicted theoretically in 1975 by Kip Thorne and Anna Zitko. In a binary system where one star has exploded as a supernova, the resulting neutron star can eventually be engulfed by its companion as the companion expands into a red giant. The neutron star sinks to the center of the giant, where it would accrete material from the core and produce unusual nuclear reactions not possible in normal stellar cores. The observable consequence would be unusual chemical abundances, specifically enrichment in elements like rubidium, molybdenum, and lithium on the surface of the giant star. In 2014, a candidate Thorne-Zitko object was identified in the Small Magellanic Cloud, HV 2112, a giant star with exactly the unusual chemical signatures predicted. The confirmation is not yet definitive, but the existence of such objects in the Milky Way and its companion galaxies is considered plausible. The idea of a neutron star embedded inside a larger star, feeding on it from the inside, is one of the most genuinely strange structures in astrophysics. On the topic of strange structures, let us consider the Boomerang Nebula, the coldest known natural place in the universe. It is a protoplanetary nebula, a star in the process of ejecting its outer layers before they form a conventional planetary nebula, located about 5,000 light-years away in the constellation Centaurus. The Boomerang Nebula has a temperature of 1 Kelvin, minus 272 degrees Celsius, just 1 degree above absolute zero. This makes it colder than the cosmic microwave background radiation, the afterglow of the Big Bang, which has a temperature of about 2.7 Kelvin. The Boomerang Nebula is colder than the average temperature of the universe itself. Its extraordinary cold is produced by the rapid expansion of gas expelled from the central star at approximately 500,000 kilometers per hour. This expansion cools the gas in the same way that a rapidly expanding gas cools when released from a pressurized container, the same principle behind refrigeration. Within the Milky Way, we have a place colder than the average temperature of the whole universe. The galaxy contains extremes in every direction. At the other extreme of temperature, there are neutron stars with surface temperatures in the tens of millions of Kelvin, white dwarfs initially at temperatures of over 100,000 Kelvin, and the plasma in the jets emanating from active galactic nuclei and the accretion disks of black holes, where temperatures can reach into the trillions of Kelvin. The Milky Way spans an extraordinary range of physical conditions, from the coldest natural places in the universe to some of the hottest, from the emptiest voids to the densest neutron star cores, from the gentlest radiation environments to the most lethal. It is a cosmos unto itself, a universe of universes, containing almost everything physics allows. We should talk about what happens when you fall into Sagittarius A star, because it is one of those thought experiments that combines physics, philosophy, and the most extreme environments conceivable. From the perspective of someone watching you fall toward the black hole from a safe distance, you would appear to slow down as you approach the event horizon, your image increasingly redshifted, shifted toward the red end of the spectrum by the extreme gravitational field, and eventually frozen at the event horizon, growing dimmer and redder as the photons reaching the observer become increasingly infrequent and low energy. You would appear to never quite cross the event horizon, gradually fading to invisibility over an enormous amount of time. But from your own perspective, if you were falling freely, you would cross the event horizon without any locally dramatic experience. You would pass through a boundary that has no physical marker, no surface, no wall. General relativity tells us that the event horizon is not a physical surface but a mathematical boundary, a surface of no return. Once across it, the future direction of spacetime points inexorably toward the singularity at the center, in the same way that time always points inexorably toward the future in normal spacetime. You cannot avoid the singularity any more than you can avoid tomorrow. And at the singularity, the curvature of spacetime becomes infinite, the laws of physics as currently formulated break down, and we simply do not know what happens. It is a genuine frontier of physics, a place where our best theories tell us they cannot go, and what lies beyond is unknown. The information paradox. The question of what happens to the information about everything that has ever fallen into a black hole, which seems to be destroyed at the singularity but which quantum mechanics insists cannot be destroyed, is one of the deepest unresolved problems in theoretical physics. Stephen Hawking spent decades thinking about it. The current leading proposals involve subtle correlations in the Hawking radiation emitted by the black hole as it evaporates, or modifications of the physics near the event horizon in ways that encode the fallen information in some form. The debate is far from resolved. Sagittarius A star, at the center of our galaxy, is at the heart of one of the most profound open questions in fundamental physics. Now let us bring all of this back to the human scale for a moment, because the Milky Way is not just an abstract object of scientific study. It is our home. It is the backdrop of every human experience that has ever occurred. Every act of love, every war, every great work of art, every scientific discovery, every birth and every death has occurred within the gravitational embrace of this galaxy. Every human being who has ever lived has looked up at its glow, whether or not they knew what they were seeing, and felt something. Awe, wonder, fear, longing, a sense of vastness and their own smallness. The Milky Way is the oldest backdrop to human consciousness, older than any civilization, older than our species, older than the Earth itself. And now, for the first time in human history, we are beginning to understand it. Not just to see it and wonder, but to actually understand it, to know its age, its size, its structure, its history, its future. To know that it is cannibalistic and ancient and violent and beautiful and full of extreme objects that push the limits of physics. To know that we are inside it, that we owe our very existence to its chemical history, that we will be consumed with it in the Andromeda merger and will end with it in the cold dark of a trillion years hence. To know that somewhere among its 400 billion stars, there may or may not be other minds asking these same questions, looking out at the same galaxy, wondering if they are alone. This knowledge is new. It is fragile. It is purchased at the cost of centuries of patient, painstaking scientific effort by thousands of astronomers and physicists and engineers who dedicated their lives to looking up and trying to understand. It is one of the greatest achievements of the human mind. And it is still incomplete. There is still so much we do not know about the Milky Way. We do not know the precise nature of dark matter. We do not know the exact structure of the far side of the galactic disk, hidden from us by the zone of avoidance. We do not know the full history of the galaxy's mergers and accretion events. We do not know whether life exists anywhere else within it. We do not know why the star formation rate in the central molecular zone is so anomalously low. We do not know the precise origin of the highest energy cosmic rays. We do not know the details of how the Fermi bubbles formed. We do not know the fate of the Magellanic Clouds. We do not know what exactly lives at the centers of globular clusters like Omega Centauri. We do not know whether the warp of the galactic disk is truly driven by the Magellanic Clouds or by some other mechanism. We do not know with certainty what happened to all the mass in the universe that has not been detected as either ordinary matter or dark matter, the so-called missing baryons problem. We do not know whether there are more exotic compact objects, strange quark stars, boson stars, primordial black holes, lurking in the galactic halo. We do not know the full extent of the stellar streams in the halo and what they reveal about the galaxy's merger history. We do not know whether the Sagittarius dwarf galaxy will be fully consumed in the next orbit or whether remnants will persist. We do not know whether the subtle chemical anomalies in some halo stars are truly the fingerprints of population 3 supernovae or reflect some other process. And we certainly do not know whether, somewhere among the galaxy's billions of planetary systems, another pair of eyes has been looking back at us. But here's what makes this ignorance not discouraging but thrilling. We are in the middle of the greatest era of astronomical discovery in history. The combination of Gaia, ALMA, the Event Horizon Telescope, the James Webb Space Telescope, the Rubin Observatory's Legacy Survey of Space and Time, the Square Kilometer Array coming online in the near future, LISA, the Laser Interferometer Space Antenna, for gravitational wave astronomy in space. These instruments and their successors will answer some of these questions and, inevitably, raise new ones we have not yet thought of. Every great answer in science opens 10 new questions. The more we learn about the Milky Way, the more we find we do not know. And that, perhaps, is the most reliable sign that we are doing science right. The James Webb Space Telescope, launched in December 2021, has already begun producing results of extraordinary quality that are relevant to the Milky Way and its context. Its infrared sensitivity and resolution allow it to peer through dust to see stellar nurseries and the earliest stages of star formation in unprecedented detail, to observe the chemistry of planetary atmospheres, to look back at the earliest galaxies in the universe and compare them to the present-day Milky Way. Webb has already imaged stellar nurseries like the Carina Nebula and the Pillars of Creation in the Eagle Nebula in a resolution and detail that reveals structures and young stellar objects previously invisible. Its observations are rewriting our understanding of star formation and the conditions in molecular clouds. Let us now consider a theory, and it is important to emphasize that this is a theoretical framework, not established fact, known as the galactic panspermia hypothesis. This is the idea that life, once it arises on a planet anywhere in the galaxy, can spread to other planets through the ejection and capture of rocky material during asteroid impacts, through interstellar comets, or through some other mechanism. If this is true, then life in the Milky Way might not have originated independently on each life-bearing planet, but might instead share a common ancestry, traced back to one or a few original emergence events, from which life spread throughout the galaxy over billions of years. Under this scenario, life on Earth might be related to life on other worlds, not as cousins to other Earth life, but in the deeper sense that both descended from a common ancestral biology seeded from the same source. This idea is highly speculative but not dismissed by serious scientists. The discovery of Mars meteorites on Earth, rocks blasted off Mars by asteroid impacts and subsequently captured by Earth's gravity, demonstrates that material can indeed travel between planets. Whether microorganisms could survive the interstellar journey is far less certain, but it cannot be ruled out, particularly if they were protected deep within a large rock. Some researchers have even speculated that life might be particularly common near the galactic center, where stellar density is higher and the chemical enrichment is more advanced, and that life might have originated there billions of years before it arose on Earth, spreading outward through the galaxy over time. If such a galactic life front exists, we might be on its leading edge, one of the more recently colonized worlds. Or we might be anomalously early, one of the first worlds to host life in this part of the galaxy. There is simply no way to know with our current knowledge. One of the things that makes this all so extraordinary is that we are asking and trying to answer these questions right now, in real time, with instruments we have only recently built, looking at a galaxy we have only recently mapped, in a universe we have only recently begun to understand. The Milky Way has existed for 13.6 billion years. Human civilization is perhaps 10,000 years old. Modern astronomy is perhaps 400 years old. The scientific understanding of the Milky Way as a galaxy, one among billions, is barely a century old. In the cosmic time frame of the galaxy, our awareness of what we are part of has just flickered into existence. We are infants, cosmically speaking, who have just opened our eyes and found ourselves inside something vast and violent and ancient and beautiful, and we are just barely beginning, to understand what we are seeing. Every time you look up at the night sky, on a clear night away from city lights, when the Milky Way is visible as that river of light stretching across the sky, you are looking at something that has been there for 13 billion years, that has survived the deaths of billions of stars and the mergers of dozens of galaxies, that harbors at its heart a black hole 4 million times more massive than the Sun, that is right now in the process of consuming 2 dwarf galaxies and is on a slow collision course with Andromeda. You are looking at your home. Not the cozy, human-scaled home of a house or a city or even a country, but a home vast enough to contain 400 billion suns and all the planets and all the possible histories orbiting each of them. And you are looking at it from the inside. From a small rocky planet, orbiting one of those 400 billion suns, in a minor spiral spur, in the quiet suburbs of a galaxy that is anything but quiet when you look closely. You are here, alive, wondering, in the middle of all of this, and that fact alone, that the universe has arranged itself such that something inside it can be aware of the whole, can look at the galaxy it lives in and say, I understand this, I know where I am, I know what this is perhaps the most extraordinary fact that has ever existed. Now ask yourself one final question, and hold it, and do not try to resolve it quickly, because it does not have a quick answer. If the Milky Way has been here for 13.6 billion years, and our awareness of it has existed for a fraction of that time, what might we come to understand in the next billion years if we survive? What might we see? What might we discover? What is the Milky Way still hiding from us? In its far side and its dark matter halo and its ancient stellar archaeologies and its distant, silent, possibly inhabited worlds. We do not know. And that is not a failure. That is an invitation. The galaxy is 13.6 billion years old, and we have had 100 years to start understanding it. The story is just beginning. The Milky Way is a barred spiral galaxy approximately 100,000 to 160,000 light-years in diameter, containing between 100 billion and 400 billion stars, with a supermassive black hole at its center, wrapped in a dark matter halo, warped and rippled by gravitational interactions, actively consuming smaller galaxies, hurtling through the cosmos at millions of kilometers per hour toward a collision with Andromeda, harboring among its countless worlds a small blue planet where, for the first time in its history, something looked up at it and asked, "What are you?" We asked the question. We have been gathering the answer for centuries. And the answer so far is this: you are more extraordinary than you knew, more ancient than you imagined, more violent than you appeared, more beautiful than can be described, and you are our home. And we are just getting started. There is a particular quality to the night sky in the southern hemisphere, in a place like the Atacama Desert in Chile or the outback of Australia, far from any city, on a moonless night, where the Milky Way rises from one horizon to the other and the southern constellations will slowly overhead. In those places, you can see the Magellanic Clouds as detached, bright patches of the Milky Way. You can see the dark patches within the galactic band, the coal sack, the Great Rift, which are not gaps in the stars but foreground clouds of dust and gas that absorb the light of more distant stars. You can, if you know where to look, find the direction of the galactic center with your naked eye, toward Sagittarius, where the band of the Milky Way is brightest and widest. You can experience, in those moments, something that all of human history up until the last 100 years shared. The direct, visceral sense of the galaxy's presence, its light falling on your retinas, its photons, some of them 26,000 years old, some of them from the Magellanic Clouds, 160,000 years old, actually entering your eyes and triggering the electrochemical signals in your visual cortex that constitute the experience of seeing. Light that traveled from the galactic center 26,000 years ago, when anatomically modern humans were hunting mammoths and painting in caves, has just entered your eyes. You have just seen the past. You have just received a message from the heart of the Milky Way, posted 26,000 years before you were born, and delivered to you tonight. That is the Milky Way. That is your home. And there is nowhere else in the universe you would rather be to receive that message, because you are the only thing in the Milky Way, as far as we currently know, that can recognize what it is, appreciate what it means, and feel the weight of what it says. What it says, ultimately, is this: you are here. Against all the odds, against the violence and the radiation and the cold and the vast empty distances and the million ways the galaxy could have prevented you from existing, you are here.